So now let's finally just end this video off with just a brief mainstream history of Fibonacci and more. Very interesting stuff. Yeah, it's been a habit that I've been going over in my earlier videos. Whenever I cover a concept in mathematics, I would like to go discuss the mainstream history behind it and behind the people behind it. Very interesting stuff, so I'll continue with that theme. So let's dive into here. So on Wikipedia for Fibonacci, let's read up on him. So Fibonacci, born in 1175 Common Era or AD, and then he died around 1250 Common Era. Was an Italian mathematician from the Republic of Pisa, considered to be the most talented Western mathematician of the Middle Ages. The name he is commonly called Fibonacci, or Italian Fibonacci, was made up in 1838 by the Franco-Italian historian Guillaume Liber or Libri, and is short for Filius Bonacci, son of the Bonacci, and he also is known as Leonardo Bonacci, Leonardo of Pisa, Leonardo Pisano Bigello, or Leonardo Fibonacci. So yeah, so the name is apparently made up. Very, very interesting. But anyways, going further, Fibonacci popularized the Hindu-Arabic numeral system in the Western world, primarily through his composition in 1202 of Liber Abaci, Book of Calculation. He also introduced Europe to the sequence of Fibonacci numbers, which he used as an example in Liber Abaci. So here's an image, here's a statue of him, zoom in there, very interesting statue of Fibonacci. He's got a pretty nice robe. It's going over, so statue of Fibonacci 1863 by Giovanni Paganazzi in the Campanato di Pisa. So you're born 1175 Common Era in Pisa in Italy, and he died most likely 1240 to 50, most likely in Pisa. Occupation mathematician, and he was known for Liber Abaci, popularizing the Hindu-Arabic numeral system in Europe, Fibonacci numbers, and his parents was Guglielmo. That's hard to pronounce. So history: Fibonacci was born around 1175 to Guglielmo, a wealthy Italian merchant, and by some accounts the consul for Pisa. Guglielmo directed a trading post in Bugia, a port in the Almohad dynasty's Sultanate in North Africa. Fibonacci traveled with him as a young boy, and it was in Bugia, now Bajaji, Algeria, that he learned about the Hindu-Arabic numeral system. So yeah, Fibonacci traveled extensively around the Mediterranean coast, meeting with many merchants and learning about their systems of doing arithmetic. He soon realized the many advantages of the Hindu-Arabic system. In 1202, he completed the Liber Abaci, Book of Abacus, or Book of Calculation, which popularized the Hindu-Arabic numerals in Europe. Fibonacci became a guest of Emperor Frederick II, who enjoyed mathematics and science. In 1240, the Republic of Pisa honored Fibonacci, referred to as Leonardo Bigello, by granting him a salary in a decree that recognized him for the services that he had given to the city as an advisor on matters of accounting and instruction to citizens. The date of Fibonacci's death is not known, but it has been estimated to be between 1240 and 1250, and most likely in Pisa. So Liber Abaci 1202 is the main article if you want to go read that on Wikipedia. So in the Liber Abaci 1202, Fibonacci introduced the so-called modus interum method of the Indians, today known as a Hindu-Arabic numeral system. 1202, so his birthday, he was born in 1175, so I believe that's about 27 years old. It's interesting. So the book advocated numeration with the digits 0 to 9 and place value. The book showed the practical use and value of the new Hindu-Arabic numeral system by applying the numerals to commercial bookkeeping, converting weights and measures, calculations of interest, money changing, and other applications. The book was well received throughout educated Europe and had a profound impact on European thought. No copies of the 1202 edition are known to exist. The 1228 edition, however, first section introduces the Hindu-Arabic numeral system and compares the system with other systems such as Roman numerals and the methods to convert the other numeral systems into Hindu-Arabic numerals. Replacing the Roman numeral system is ancient Egyptian multiplication method, and using an Abacus for calculations with a Hindu-Arabic numeral system was an advance in making business calculations easier and faster, which led to the growth of banking and accounting in Europe. The second section explains the uses of Hindu-Arabic numerals in business, for example, converting different currencies and calculating profit and interest which were important to the growing banking industry. The book also discusses rational numbers and prime numbers. So here's a page from his 1228 edition of the book. So a page of Fibonacci's Liber Abaci from the Bibliothèque Nationale de Firenze, shown in box on the right. The Fibonacci sequence with a position in the sequence labeled in Roman numerals and a value in Hindu Arabic numerals. And and I believe there's a 1228 edition, but it could be a different edition. But anyways, so we have scanned copy here, and so I believe these ones would be the Roman numerals. I'm not sure which ones. Those are probably some of these ones, different lettering here, and then I believe these are the Indian numbers similar to ours, 1, 2, 3, 4 to 9. I believe that's a 144. I'm not sure. I believe they're just different numbers for theirs. But yes, very, very interesting stuff here. Let's just continue further into this. So now let's look at the Fibonacci sequence, and there you can read more main article Fibonacci number. I'll cover that actually in a bit. So Liber Abaci posed and solved the problem involving the growth of a population of rabbits based on idealized assumptions. The solution generation by generation was a sequence of numbers later known as Fibonacci numbers. Although Fibonacci's Liber Abaci contains the earliest known description of the sequence outside of India, the sequence has been noted by Indian mathematicians as early as the 6th century. Fascinating. In the Fibonacci sequence of numbers, each number is the sum of the previous two numbers. Fibonacci began the sequence not with 0, 1, 1, 2 as modern mathematicians do, but with 1, 1, 2, etc. He carried the calculation up to the 13th place, and then 14th in modern computing, because there's that 0. Yeah, the 0 adds an extra layer there. So that is 2, 3, 3. Though another manuscript carries it to the next place, 1, 1, 2, 3, 5, 8, 13, 21, 34, 55, 89, 144, 233, 377. And Fibonacci did not speak about the golden ratio as a limit of the ratio of consecutive numbers in the sequence. Very interesting, yes, and I'll explain the golden ratio soon, as I illustrated earlier above as well. So legacy. In the 19th century, a statue of Fibonacci was constructed and raised in Pisa. Today it is located in the western gallery of the Camp Ozzanato historical cemetery on the Piazza di Miracoli. Interesting stuff here, guys. So here's just an image from him I found on a mainstream news site, express.co. UK is drawing or a photograph of him. So this is Fibonacci. I believe he was 27 when he wrote that book. It's probably younger image of him. So now let's quickly go over some of the mainstream history and overview of the Fibonacci sequence and its close relationship with the golden ratio. Yeah, hashtag fascinating stuff. So going further. Yeah, so it's from Wikipedia, Fibonacci numbers. So in mathematics, the Fibonacci numbers are the numbers in the following integer sequence called the Fibonacci sequence, and characterized by the fact that every number after the first two is the sum of the preceding one. So 1, 1. So 1, 1, then we have 2. Then again, we have 2 plus 1 is 3, 2 plus 3 is 5, 3 plus 5 is 8, and so on. So we have it all like that. Alright, so now often, especially in modern usage, the sequence is extended by one more initial digit, and that's adding a 0 there. So again, this 1 is the sum of 0 and 1, and so on. So by definition, the first two numbers in the Fibonacci sequence are either 1 and 1 or 0 and 1, depending on the chosen starting point of the sequence, and each subsequent number in the sum of the previous two. Is the sum of the previous two. So the sequence Fn of Fibonacci numbers is defined by the recursion relation, as I went over, and that is basically Fn equals Fn minus 1 plus Fn minus 2. Or F0 equals 1. Actually, whoops, I just thoughtlessly read that one on. So yeah, so it's this sequence with seed values, or the initial values, F1 equals 1 and F2 equals 1. Or for modern usage, or modern computing usage, usually it's F0 equals 0 and F1 equals 1. And now here is a tiling with squares whose side lengths are successive Fibonacci numbers. So we have 1, 1, and 2, then go to side 3, then you go to 5, then you go to 8 like this, and then you go to 13. It's very interesting. These are the side lengths. Yeah, so I believe these are the, these are squares, so each one is 13, so this is going to be 13 like that. And so on. That is very interesting how they all line up perfectly like that. Then it goes all the way to 21, and 21 lines up with that as well. That's actually very, very amazing. Yeah, so yeah, I just want to add a quick note there. So yeah, very interesting how the side lengths match up with the previous squares as they spiral around. Very interesting like that. That's actually quite fascinating stuff. And here's further. Here's a Fibonacci spiral, which is an approximation to the golden spiral created by drawing circular arcs connected at the opposite corners of squares in the Fibonacci tiling. So these are the opposite corners, like that goes to here, this goes to here, and you start off like that. And very, very fascinating stuff indeed. And this one uses squares of size 1, 1, 2, 3, 5, 8, 13, 21. Very fascinating stuff. So Fibonacci numbers appear to have first arisen in perhaps 200 BC in work by Pingala on enumerating possible patterns of poetry formed from syllables of 2 lengths. The Fibonacci sequence is named after Italian mathematician Leonardo of Pisa, known as Fibonacci. His 1202 book, Liber Abaci, introduced the sequence to Western European mathematics. Although the sequence had been described earlier in Indian mathematics, the sequence described in Liber Abaci began with f1 equals 1. Fibonacci numbers were later independently discussed by Johannes Kepler in 1611 in connection with approximations to the pentagon. That's very fascinating too. Actually, gotta look into that. So their reoccurrence relation appears to have been understood from the early 1600s, but it has been only in the past very few decades that they have in general become widely discussed. Interesting. So they are intimately connected with the golden ratio. For example, the closest rational approximations to the golden ratio are 2 over 1, 2 over 1, 3 over 2, 5 over 3, 8 over 5, and so on. That's fascinating. So there you see the Fibonacci numbers there: 2, 3, then 5, then 8, and so on. That's actually very amazing. So Fibonacci numbers appear unexpectedly often in mathematics, so much so that there is an entire journal dedicated to their study, the Fibonacci Quarterly. Applications of Fibonacci numbers include computer algorithms such as the Fibonacci search technique and the Fibonacci heap data structure, and graphs called Fibonacci cubes used for interconnecting parallel and distributed systems. Very, very fascinating. They also appear in biological settings such as branching leaves, phyllotaxis, the arrangement of leaves on a stem, the fruit sprouts of a pineapple, the flowering of an artichoke, an uncurling fern, and the arrangement of a pine cone's bracts. So yes, you'll see this everywhere. And the Fibonacci numbers are the sums of the shallow diagonals shown in red of Pascal's triangle. So notice how this goes up to 1. So this one here, if you have 1, this is going to be 1, the sum of 0 and 1. And this one here, sum of 1 and 0. And then if you have over here 2, it's going to be sum of 1 plus 1 is 2. And then the 3 is going to be 1 plus 2 is 3. The 6, as you can see, is the sum of the top 2. So 3 and 3, 6. So you go to here 35, 20 plus 15 is 35. And here if you sum all these shallow angles, it's actually pretty amazing. Shallow diagonals, you get 1. Then you get 1 again. Then you get here 2. Then you get this. Wow, that's amazing. 2, 1, so that's 3, then 5, 8, 13, 21, 34, 55. So yes, that's absolutely fascinating. So now let's look at the golden ratio and go over here. And let's read up on this. So in mathematics, two quantities are in the golden ratio if the ratio is the same as the ratio of their sum to the larger of the two quantities. And the figure on the right, it's actually below, illustrates a geometric relationship. Expressed algebraically for quantities a and b with a greater than b greater than 0, we have over here a plus b over a. If it equals to a over b, then this is by definition phi. This is phi, or the golden ratio, where the Greek letter phi, written like this, lowercase phi or phi, represents the golden ratio. It is an irrational number with a value of, and this is exactly the one I calculated in exercise 5. So 1 plus square root 5 divided by 2 equals 1.61803398887. And I mean, so this is the limit of the ratio of successive numbers of the Fibonacci sequence in exercise 4. And now remember, exercise 4, I just want to scroll up quickly because I think I may have mentioned earlier that the limit of the sequence is golden ratio, but that's actually not the case. It's the ratio. So here, remember here, so we let an equals to fn plus 1 divided by fn, like that. So that's the ratio of the successive terms of the Fibonacci sequence. But the Fibonacci sequence, the limit just keeps getting larger and larger, so it's infinity. So yes, so it's the ratio. And I showed here, then when you do the ratio, it becomes like this, 1.618. So yes, fascinating stuff indeed. Let's just go back over here to the golden ratio. So the golden ratio is called the golden mean or golden section, in Latin sectio aurea. Other names include extreme and mean ratio, medial section, divine proportion, divine section, or Latin sectio divina, golden proportion, golden cut, and golden number. Mathematicians since Euclid have studied the properties of the golden ratio, including its appearance in the dimensions of a regular pentagon. So you have to dig into that. It's very fascinating. And in a golden rectangle, which may be cut into a square, and a smaller rectangle with the same aspect ratio. The golden ratio has also been used. It has been used to analyze proportions of natural objects such as as well as man-made systems such as financial markets, in some cases based on dubious fits to data. So yes, interesting. So the golden ratio appears in some patterns in nature, including the spiral arrangements of leaves and other plant parts. Some 20th century artists and architects, including Le Corbusier and Salvador Dali, have proportioned their works to approximate the golden ratio, especially in the form of the golden rectangle, in which the ratio of the longer side to the shorter side is the golden ratio. And believing this proportion to be aesthetically pleasing. So here is line segments in the golden ratio. So you have A and B, where the summation A plus B divided by A is, so A plus B is to A as A is to B. So it's the same ratio. And here's the golden rectangle with longer side A and shorter side B. When placed adjacent to a square with side lengths A and B, to side lengths A, will produce a similar golden rectangle with longer side A plus B and shorter side A. So yes, we have a golden rectangle over here, so A plus B over A. That's the golden rectangle, as well as A over B. So A over B, golden rectangle, and then the overall one is going to be golden rectangle. Put both of them together. And also what you could do here now, what I'm going to do is, well, I'm going to divide this out by B. So if we divide it out by B, I'll just divide every single side. We're going to get a smaller rectangle, obviously, just to illustrate it. So what we'll have is B over B is 1. A over B is phi. And then over here is going to be, well, phi. A over B. And this is, well, A over B is equal to phi. So phi, so we have a square phi like that, and this is phi like that. So yes, there's one. That's phi. So fascinating stuff. So going further, now relationship to Fibonacci sequence. The mathematics of the golden ratio and the Fibonacci sequence are intimately interconnected. The Fibonacci sequence is 1, 1, 2, 3, 5, 8, 13, 21, 34, 55, 89, 144, 233, 377, 610, 987. And a closed form expression for the Fibonacci sequence involves the golden ratio, and you can write it like this: Fn equals 2, and you simplify phi n minus negative phi to the power of negative n divided by a square root 5. So the golden ratio is the limit of the ratios of successive terms of the Fibonacci sequence, or any Fibonacci-like sequence as originally shown by Kepler. So the limit as n approaches infinity of Fn plus 1 divided by Fn equals to phi, as I showed. This is exactly exercise 4. In other words, if a Fibonacci number is divided by its immediate predecessor in the sequence, the quotient approximates phi. For example, 987 over 610 is going to be roughly equal to phi, like that, and so on. So for example, 2 over 1 is going to be, well, it's going to be 2. So then 3 over 2 will be 1.5. So it gets closer and closer to that number. And then 5 over, what's 5 over 3? That is, let's see what 5 over 3 is. So I'm going to type it in quickly. 5 over 3 equals 1.667, and so on. So that's fascinating. Then 8 over 5 equals 1.6. So yes, you'll eventually get closer and closer. And there it is, numbers in the in the later parts in the Fibonacci sequence. So it's fascinating stuff indeed. So these approximations are all alternately lower and higher than phi, and converge to phi as the Fibonacci sequence increases. So yes, they alternate. That's pretty amazing. Let me just type that in over here, actually. Yeah, note here, I just want to illustrate this further. So MES note, here's the Fibonacci sequence, and here is phi. So let's just remove this dot. Yeah, so put phi over there, and let's see what happens when you do the term. So 1 over 1, that is obviously... So yeah, now we have over here, so 1 over 1 is 1, 2 over 1 is equal to 2, and then going further here, we have 3. So then the next one is is 3/2. Let's see how it looks like. And then next one is we have it's 5/3. And the next one is we have, let's remove the spaces. So now we have, next one is 8/5 equals 1.6. And then we have next one is 13/8. And the next one we have is 21/13. So yeah, you can see it's it's going above and below the 1.618. So initially it's below, above, below, above, below, and then this one's going to be above, and then this is below, and then the next one, this is very, very fascinating stuff. The next one is 34 divided by 21. Now we have, this is above 1.618, and then we have 55/89 equals, the other way around, we have 55/34. Over 34, and this equals below, and then we have next one 89, 89/55 equals 1.618. That's a bit higher, so there's 1.6182, and then keep going on. This is pretty fun. So 114/89 equals 1 point. Actually, that's off. So 144, like that. So 1.618, and then 233/144. It's getting pretty cool. And then 377 divided by 233 equals 1.618. And then let's see, I think my calculator is rounding up. 610/377 equals, it's just rounding up, and so on and so on. Yeah, so it actually just rounds up and so on. But what we could do here is now, I'll put a space here. So instead of, I could just type in pi, and also you could just put equals, and equals there. This is capital letter, I just made it capitals. And there it is, there is phi. Fascinating stuff indeed. Now I'll put erase the last digit, so because it sums up, and just put a dot, dot, dot. Because otherwise it would round up. So because 8, 9, and there's the 5 actually. Actually, that's not the exact phi. Let's see what the exact phi is. And the exact phi is 887. We have 887. Yeah, that's already rounded up. So anyways, that was just a sidetrack. Just wanted to get in those. I didn't realize it alternates like that. And it was very fascinating stuff. So now let's look at the golden angle. So in geometry, the golden angle is the smaller of the two angles created by sectioning the circumference of a circle according to the golden ratio. That is, into two arcs such that the ratio of the length of the larger arc to the length of the smaller arc is the same as the ratio of the full circumference to the length of the larger arc. Very, very fascinating. So yeah, basically, we're going to do the same thing with arc lengths. So the total to the larger, and it's the larger to the smaller. So that's all it is. So algebraically, let A plus B be the circumference of a circle, divided into a longer arc of length A and a smaller arc of length B, such that, so you have two arcs that form one full circumference, and then we have the golden ratio over here equals to phi. And the golden, golden angle here. The golden angle is the, actually no, the golden angle is not going to be like that. I mean, this is phi, this ratio is phi, but then the golden angle is going to be the angle subtended by the smaller arc of length B. It measures approximately 137.5077, etc. Or in radians 2.3999, and so on. It's fascinating stuff. And the name comes from the golden angle's connection to the golden ratio. The exact value of the golden angle is, and you can type it here, 360 divided by 1 minus 1 over phi. Oh yeah, let's put this phi, that's phi. And so on. And you get this degrees about 180 times 3 minus square root 5, and so on, or 360 divided by phi squared, or in radians 2 pi over phi squared. So yes, fascinating stuff indeed. So here it is, if you were to draw this out. So where the equivalents follow from well-known algebraic properties of the golden ratio. So here's the golden angle. Is the angle subtended by the smaller red arc. So there is our 137 ... degrees. When two arcs that make up a circle are in the golden ratio. So there we're going to have the golden ratio across there. So again, A plus B over A equals A over B. So it's fascinating stuff indeed. And now here's an example of the angle between successive florets and sunflowers is the golden angle. So if you have one, it's going to be 137. Then the next one, so there's 1, there's 2, there's 3, and so on. Then there's going to go to the 4 here. Then go 4 is going to go to the 5. 5 is going to go to the 6. 6 is going to go to the 7, 8, 9, 10. Fascinating, fascinating stuff. So as you see it everywhere. So the angle between them are all going there. So now let's look at the golden spiral. So in geometry, a golden spiral is a logarithmic spiral whose growth factor is phi, the golden ratio. That is, a golden spiral gets wider or further from its origin by a factor of phi for every quarter it turns. And yeah, this is in polar coordinates. A golden spiral with initial radius 1 has the following polar equation: r equals phi to the power of the angle theta times 2 over pi. That's in radians. So yes, then what you end up having is this spiral across like that, where, again, where's the definition here? So it gets further from the origin by a factor of phi for every quarter turn it makes. So yes, if it goes here, a quarter is going to go across there, a quarter is going to go across there, and it goes further by a factor of phi. So yes, it looks like that phi, it looks like the approximation to it, the Fibonacci spiral. So yeah, golden spiral, assuming a square has a side length of 1, the next smaller square is 1 over phi wide, the next width is 1 over phi squared. Yeah, this is the next smaller one, so yeah, each one's width is going to be 1 over phi squared and 1 over phi cubed. So on, it's very interesting stuff. And here's the Fibonacci spiral, approximates a golden spiral using quarter circles inscribed in squares of integer Fibonacci numbers, shown again, this is sort of one above, 1, 1, 2, 3, 5, 8, 13, and 21, and so on. So this looks like that spiral there. Very fascinating stuff. I can find a good comparison between the two, but maybe in later videos. So anyways, finally, let's go over some golden and Fibonacci spirals in nature and art, design, corporations, even advertising, and Fibonacci sequences, and so on. So here's a galaxy, goes spiral like that. Very fascinating stuff. There's a hurricane, and there is a flower, and there is another leaves like that going in there. There's a shell, some other leaves or some other plants like that. And here is this is the model of the spiral. And here is another flower inside. And here's even water. Water is spinning in a vortex. That's following it looks like a spiral, Fibonacci / golden ratio. And here is this a snail. Here's some grass. Hurricane from above. There's a seahorse, and so on. And these, even the sequences of tree branches. You got 1, 1, and you have 2, 3, 5, 8. Yeah, I believe these are the lengths. This one has 1, this one has 2, this one has 3, then it has 5, then it has 8, and so on, and each one breaks up into it like that, and so on. Very fascinating stuff. I'm not exactly sure about the details, but yes, very fascinating. Here's some pineapples grow in a numerical sequence as well, and here's how hard to zoom in. So 8 parallel rows. So it has 8 parallel rows this way of scaling spiral gradually, and it has 13 parallel rows spiraling at a medium slope like this, and it also has 21 parallel rows of scale spiraling steeply all the way across. Fascinating stuff. And you have 1, 2, 3, 5, and then there's 8, 13, 21. And consider the drawing of a pineapple here, where we have numbered the hexagons. The numbering has been done by the following rule. The lowest hexagon was assigned to 0, 0, and then the next higher gets a 1. Remember, this continues on the backside, not visible in the picture. Then the next higher is assigned the number 2, and so on. Notice the hexagon 42 is slightly higher than hexagon 37. Yeah, whereas the 42 is 42 is slightly higher than 37. And basically, yeah, right here you should be able to identify 3 distinct spirals. One will have the hexagon 0, 5, 10. So where is the 0, 5, 10? So 0, 5, yeah, 10. I believe the 10 is on this side there. And the spirals like that. The second will have hexagon 0, 13. So there's a 0, 13, 26 going upwards like that. And the third will have will include 0, 8, 16. So 0, 8, 16. So basically similar to one above, we have a horizontal, we have a medium slope, and then we have a very steep slope up top there and there. And now look at the common difference between the spirals, and you will find a difference between 5, 18, 13. Yeah, 5, 8, and 13. So there's 5 this way, there is, and this one is a bit smaller than the other ones, and this one's going to be 8. It's going to be 13 across. It's going to be 13 across there. This should be. So this one follows a 5, 18, 13 over here, but then this pineapple is, I believe, is bigger relative to its the hexagons, and those go 8, 13, 21. So anyways, that's very interesting. Yeah, a very interesting pineapple Fibonacci sequence. So yeah, there's this way, and then there's the vertical one. So yes, count them up next time you eat a pineapple. Here's an egg, also Fibonacci sequence across there. Let's see, here's even continents. You could see Africa like that, starting from there and goes all the way down. Very fascinating stuff. There's a Mona Lisa. Very fascinating stuff indeed. So going further, this is Sonic the Hedgehog. And there's even websites can also have it visually set up like that. So little tabs on top there, and then scrolls over for the big main stuff that you got to look at, the main article. So there's National Geographic. You could also see it has one there. Here's another website here. And yeah, so there it is, to set up in all these blocks and Fibonacci blocks. And even here, this is even movie covers. You can see, yeah, you can see the kind of spiral here across, and there's a spiral across there, and yeah, it's very, very fascinating stuff. And here is a Dream Piano advertisement. There it is, the Fibonacci sequence as well. It just it looks cool, and yeah, I believe Apple logo probably has it too. Yes, very interesting stuff here. I haven't confirmed, but it looks like it. You got a bunch of spirals here. And yeah, and even a ball thrown in a wet tennis ball like that, spiraling across. There's Fibonacci in the waves. There's Fibonacci hurricane, galaxies, and even Trump's hair. So yes, yeah, pretty cool stuff.